Molecular orbital theory. Okay, this is the most complicated bonding theory we're going to cover. In valence bond theory, the electrons in the bonds were still localized between the two atoms. In molecular orbital theory, we have electron delocalization. So instead of looking at orbitals just on individual atoms, even hybrid orbitals, we're going to calculate orbitals for the whole molecule. So that's easier said than done. The Schrödinger equation, even for a simple molecule, is impossible to solve. And so they have to do kind of a trial and error iteration method where they make a trial function and stick that in and then tweak it. And it uses very powerful computers to calculate all of this and optimize for the lowest energy. And of course, this is us trying to figure out what nature is doing. Nature's always better at minimizing the energy of an orbital. So an LCAO is a linear combination of atomic orbitals. And this is a weighted linear sum of the valence atomic orbitals of the atoms in a molecule. This is the simplest of the trial functions that works reasonably well. And this combines the valence atomic orbitals of all the atoms in the molecule together. Where the difference here from valence bond theory is that valence bond theory hybridizes orbitals only on a single atom. And these are a combination of all the atomic orbitals in the whole molecule. So let's look at hydrogen. So we can think of one of these molecular orbitals. We're talking about a molecule of hydrogen, so it's two hydrogen atoms. One of the molecular orbitals is going to be an equally weighted sum of the 1s orbital from each atom. So if we add these together, we get something that looks like this. This has the name sigma because of its shape. If you looked from end to end, it would be symmetrical, a circle. So this is a sigma orbital, and that's partly, or actually entirely, because of the shape of these orbitals it comes from. It's a bonding orbital because adding these together lowers the energy. And an orbital that lowers the energy will be a bonding orbital. So this is called sigma 1s because its shape is symmetrical and it's formed from 1s orbitals. The next molecular orbital is made by summing the 1s on one atom with the opposite phase of the 1s on the other atom. So this is the same as subtracting. So when this happens, we get two different, what do we call those? Lobes, I guess, with a node in the middle. This is a destructive interference between these two instead of constructive interference. And so we have a node in the middle. We've got a positive phase on one side, a negative phase on the other side. This is going to be higher than energy and is not going to facilitate bonding between the two atoms. In fact, it's an anti-bonding orbital. This will be against bonding. It's also symmetrical around this axis, so it's a sigma, and it's formed from 1s orbitals, but now we put an asterisk on there to indicate that it's an anti-bonding orbital. Any questions yet? This is weird stuff. So we've taken these two orbitals, 1s and 1s on each hydrogen. We added them in a constructive way and got this. And then we subtracted them or added in a destructive way and got this. Those are the two. Again, we're going to conserve the number of orbitals. We started with two atomic orbitals. We're going to end up with two molecular orbitals. Well, do you remember we talked about constructive and destructive interference of waves? So when you have two waves that are in phase and you add them together, they get taller, right? But if you add waves that are out of phase, they cancel each other out. Okay, so that's what we're doing. It's easier to see with waves, constructive interference, destructive interference. These being three-dimensional shapes, it's more difficult to visualize what's happening. So you kind of just have to believe me, unless you want to do a computer simulation and see how those work out. I don't think anybody wants to do that. So anytime we have two atomic orbitals that we're combining into a molecular orbital, we get a bonding orbital and an anti-bonding orbital. The bonding orbital will be lower in energy because it has high electron density between the nuclei. This is the bonding orbital, and there's a lot of density here between the nuclei. That holds these nuclei together. The anti-bonding orbital is higher in energy, and it has a region of 0 electron density. It has a node between the nuclei. This is not going to encourage bonding. It will discourage bonding between these two nuclei. So we draw these diagrams to represent these because, yeah, it's nice to talk about the shapes of those molecular orbitals, but that gets very complicated very quickly. So we just draw diagrams. These are a lot like the orbital diagrams. So we have the boxes representing orbitals. Here's one hydrogen atom, and here's another hydrogen atom. And when these atomic orbitals combine into molecular orbitals, we get one bonding orbital that's lower in energy and one anti-bonding orbital that's higher in energy. Each of these orbitals can hold 2 electrons. This hydrogen atom had 1 electron. This hydrogen atom had 1 electron. So we don't have to worry about, oh, well, how did this become right side up and upside down? We're just going to start out drawing this one upside down so that these 2 electrons are going to pair together. They're going to fill the lowest orbitals first, just like when we were doing electron configurations. So those 2 electrons go into the bonding orbital. Questions? So to help us quantify whether this molecule is predicted to be stable or not, we talk about something called a bond order. And this is for diatomic molecules, and we are only going to look at diatomic molecules. We're going to look at just very simple molecules for this. The bond order is the number of electrons in the bonding molecular orbitals minus the number of electrons in the anti-bonding molecular orbitals divided by 2. So it's an average. So for H2, this is the bond order, 2 minus 0 over 2, which equals 1. Let's go back to our, not that picture. Let's go back to this picture and see how we're determining that. So the bond order is the number of bonding electrons minus, that's not a minus, minus the number of anti-bonding electrons divided by 2. So this is the bonding orbital. How many electrons in there? 2. And how many in the anti-bonding orbital? 0. So 2 minus 0, and we divide that by 2, and that equals 1. The bond order for this molecule is 1. Any questions?
Is it a number of electrons?
It's the number of electrons. So the number of electrons in bonding orbitals minus the number in anti-bonding orbitals divided by 2. Question?
So when will the antibonding not be 0?
Well, if we had another electron over here, if we had 3 electrons, then the third one would have to go up there. So the bond order for hydrogen is 1. If the bond order is positive, a chemical bond will form, because that tells us that the electrons have lower energy than they would as the 2 atoms by themselves. The higher the bond order, the stronger the bond. If you had a bond order of 2, that would be stronger than a bond order of 1. If the bond order is 0 or negative, a bond will not form. Okay? So let's look at helium, He2 molecule. Do you think that exists? What if we learned about helium? It doesn't form bonds, right? But we could still draw a molecular orbital diagram for it. So here we've got one helium atom. It has a 1s orbital with 2 electrons in it. Here's the other helium atom, 1s orbital with 2 electrons in it. When we combine these 2 atomic orbitals, we get a bonding orbital that's lower in energy and an antibonding orbital that's higher in energy. Okay? We have a total of 4 electrons from the atoms, 2 from this one, 2 from that one. We put them in just like we did when we were doing orbital diagrams before. You fill the lowest one first, 1 electron, 2 electrons, and then 3 and 4. Okay, so you start with lower energy and you move up to higher energy. Then we can calculate the bond order. The number of electrons in bonding orbitals, okay, that's these 2, minus the number in antibonding orbitals, that's those 2. So 2 minus 2 is 0, divided by 2 is 0. This is a bond order of 0. Molecular orbital theory says this molecule will not form. It doesn't. Any questions? What if we had He2 plus? So that He2 molecule that doesn't exist, and we've taken an electron off of it. I mean, we can do anything we want on paper, right? What would happen then? Well, our molecular orbitals are going to be the same, a bonding orbital and antibonding orbital. Now we have a total of 3 electrons. So here's a helium atom with 2 electrons, and this is a helium plus ion with 1 electron. There are 3 electrons because when we look at this this ion, He2 with a positive sign. It had He2, 0, has 4 electrons, and to have a positive sign, positive charge, it has to have lost an electron. So it doesn't really matter if you put the 1 electron over here or the 1 over here. You've got 3 electrons. So when we fill this in, we've got 2 in the bonding orbital and now 1 in the antibonding orbital. When we calculate the bond order, we have 2 in the bonding orbital and 1 in the antibonding orbital divided by 2, and this gives us a bond order of 1/2, which is greater than 0. So this ion is predicted to exist, and it does. It's not just floating all over the place, but it does exist. Any questions? So we approximate molecular orbitals as linear combinations of atomic orbitals. The number of molecular orbitals formed equals the number of atomic orbitals that you started with. So we're not creating orbitals, we're not destroying orbitals. If you start with 4 orbitals, atomic ones, you end up with 4 molecular orbitals. When 2 atomic orbitals combine to form 2 molecular orbitals, one will be lower in energy, that's a bonding orbital, one will be higher, that's an antibonding orbital. As we did earlier with regular orbital diagrams, we fill the lowest molecular orbitals first with up to 2 spin-paired electrons, and then we follow Hund's rule if we have molecular orbitals with the same energy. Like when we had 3 p orbitals, we put each electron in singly first with parallel spins, and then if we had to, we paired them up with opposite spins. To have a stable bond, you need a positive bond order, greater than 0, meaning you have more electrons in the bonding orbitals than in the antibonding orbitals. If you have an equal number, there is no change in energy, and the bond will not form. If you have more in antibonding, then it actually opposes forming a bond. It's only when the atoms can lower their energy by forming a bond that they will. Otherwise, they won't do it. Any questions?
So we can have negative?
You can have negative bond orders. That means that that bond will not form. That molecule doesn't exist. Okay, so here's some practice. Use molecular orbital theory to predict the bond order in H2+. is the H2 plus bond stronger or weaker than the H2 bond? So what we need to do is we need to draw this molecular orbital diagram. So we start, we start with the atomic orbitals. So here's a hydrogen, and here's a hydrogen. Now we're making H2 plus. So how many electrons are there? Only one. So I'll call this the hydrogen atom, and this will be the hydrogen ion that doesn't have any electrons. Okay? A 1s orbital and a 1s orbital. We've got two orbitals combining. They're going to form two molecular orbitals, one that's lower in energy, one that's higher in energy. So one down here and one up here. And those are, this is going to be called sigma 1s. And this one's called sigma star 1s, because this is an anti-bonding. And sometimes we draw dashed lines to show which atomic orbitals those guys came from. So atomic orbital, these are the molecular orbitals, and atomic orbital. Once we've drawn these, then we take our electrons. Here there's only one electron. And we're going to start in the lowest orbital and put that in, and it's like, well, that was fast. Now that we have that finished, we do the bond order. How many electrons in bonding orbitals? One, just this one. How many in anti-bonding orbitals? 0. And so we divide that by 2, and we get 1/2. That's the bond order, predicted bond order for He2 plus. Should this molecule exist based on this? Or this ion? Yeah, it should, because this is greater than 0. Now, the second question, is this H2 plus bond stronger or weaker than the H2 bond? It's weaker. We compare bond orders. The bond order for H2, if you go back a few slides, was 1. And this is 1/2. So here's our predicted bond order, and this bond is weaker. Any questions? Because it's closer to 0. He2 has 2 electrons in the bonding orbital. The more electrons you have in bonding and the fewer in anti-bonding, the stronger it is. Any question?
So what happens when, say, you have a bigger diatomic?
We'll get there. We'll get to bigger ones. We want to make sure we understand it with just a couple of electrons before it gets a little more complicated.
So is it only the 1s orbitals, or does it go to?
No, the P's will do it too, and the D's and the F's. We're going to just stick with the P's. So we just looked at the period 1, homonuclear diatomic molecules. Homonuclear means the nuclei are the same. It's 2 atoms of the same element. Diatomic means there's just 2 atoms. So hydrogen, H2, and He2. Now we're going to look at the period 2 homonuclear diatomic molecules. So Li2. So each lithium atom, again, we're looking at valence electrons, okay? So the valence electron for lithium is in the 2s orbital. And here's the other lithium atom, 2s orbital. Those 2s orbitals combine to form 2 molecular orbitals, sigma 2s and sigma star 2s, antibonding. We put the 2 electrons in, they go into the bonding orbital, and so this has a bond order of 1, right? Because we've got 2 minus 0 divided by 2. That equals 1. Li2 does exist in the gas phase. Any questions?
So is it like we sum the electrons and then distribute them again into the bonding?
Right. You take the number of valence electrons from each atom or ion that you're bonding together, And so I've got 1 plus 1 is 2, so I've got 2 electrons, and I'm going to fill those according to the rules that we learned earlier. Okay, let's look at Be2. Well, beryllium has 2 valence electrons, and they are in the 2s orbital. So the molecular orbital diagram is the same as for lithium. But now we have a total of 4 electrons, 2 from one beryllium atom, 2 from the other. So we put 1, 2 in the lower, and 1, 2 in the upper, and this has a bond order of 0, right? Because you take the number of bonding electrons minus the number of antibonding electrons. 2 minus 2 is 0. You divide by 2, it's still 0. Predicted to be unstable, consistent with observations. When we get to boron, now boron has an electron in the p orbital, right? So now we have to combine p atomic orbitals to make molecular orbitals. Okay? So if you remember, we have a p orbital in the x-axis and one on the y-axis going up and down, and one on the z-axis going in and out of the paper. So just so we understand what we're all doing, we decided that the x-axis is the line going between the nuclei. So this is px and px. When we combine these, we can combine them in a way that reinforces them, constructive interference, and so this blue part gets bigger. Or we can combine them in a destructive way, out of phase, or subtracting them, and so this part in the middle gets smaller and there's this node. So this is the anti-bonding orbital and this is the bonding orbital. So this is sigma 1p, sorry, 2p, it's too far away, I can't see it. Sigma 2p and sigma star 2p, because these are formed from 2p orbitals, atomic orbitals. Any questions? This is, again, a sigma orbital, a lot like the sigma bonds we saw in valence bond theory, an end-to-end overlap. It's symmetrical along the axis.
Why does the antibonding have different number of phases? I mean, different color?
Because we're adding them out of phase or subtracting them. So if you take this minus that, you end up with this. The other way to think about it is change the colors. Put red here and blue there and add them together. And then these partly disappear. They're going to cancel each other. The other electrons, the other orbitals, the 2p orbitals, they are going to add side by side, not unlike the pi bonds we saw in valence bond theory. So 2py, putting those together constructively, we get a lobe up here and a lobe down here. That's a bonding orbital. Anti-bonding, the colors are opposite, and we've got this big node in the middle. This is not symmetrical on that internuclear axis. This is a pi orbital. Pi 2p and pi star 2p. Okay? And then the other pair is going to be very similar. It's just rotated 90 degrees in space. Right? So that's up and down. And so we get this bonding where we have these pulling those guys together, and then we have anti-bonding. So this is pi star 2p and pi 2p. It's just kind of crazy, isn't it?
But we don't necessarily have to know those shapes.
You do not need to know the shapes.
I imagine
Yeah. I am hoping that seeing the shapes will give you some glimmer of how this is coming about. Yeah. But no, I'm not going to make you draw these shapes. Any other questions? So the relative energy ordering for those molecular orbitals, unfortunately, is not the same for all molecules. They do this with a computer to figure out what it is. And what we need to know is that boron, carbon, and nitrogen have a different order than oxygen, fluorine, and neon. Okay, so the normal ordering, typical energy ordering, is we've got the sigma 2p, and then the pi 2p, and then the pi star 2p, and the sigma star 2p. That's what we consider normal. And then 3 of these guys are going to be abnormal. So this is the expected order. So you've got s orbitals overlapping. We've looked at those. Makes a sigma 2s, sigma star 2s. Here you've got your 2p orbitals on each atom, and when these overlap, it makes this nice symmetrical arrangement where the sigma is the lowest and the highest, and the pi is in the middle, pi and pi star above it. Do you see the symmetry in that? So this is the expected order. What's different about this one?
Pi and sigma are switched to the bottom.
Yeah, these two are switched. So this one and this one have changed places. So now pi is lower and sigma is second and pi star and then sigma star. Okay? So this is how you remember this. Be careful now. Boron, carbon, nitrogen. If it's boron, carbon, or nitrogen, be careful now. You have to switch the order of those two. Does it matter? Yes, it matters a big deal. Okay? Because otherwise we're going to predict that things are unstable that are stable and vice versa. We're going to get our paramagnetic, diamagnetic things messed up and just, yeah. Okay? So this is normal, nice and symmetrical. Sigma's on the outside, pi's on the inside. The exception is, be careful now, boron, carbon, nitrogen, switch these two. It's the only difference. So why does this happen? Here's oxygen, fluorine, and neon, and this is the normal business. What happens with the boron, carbon, and nitrogen is that we get increased mixing of these, and that messes stuff up. So we probably don't want to dwell on the why. I think it's fine to just say, oh, it's because. Because is a great reason sometimes. So this table is showing us the molecular orbital diagrams for those last 6 elements in period 2. Boron, carbon, nitrogen, oxygen, fluorine, and neon. So boron, right? Each boron has 3 valence electrons, right? So they fill in 1, 2, 3, 4, 5, 6. The bond order here, we've got 2 in bonding orbitals down here, 2 in bonding orbitals up there. That's 4 in bonding orbitals minus 2 in anti-bonding orbitals. Divided by 2, we get a bond order of 1. Let's write that out. So for boron, we've got 4 minus 2 divided by 2, and that equals 1. So that's how we're getting this number down there. The bond energy and the bond lengths are measured experimentally, and they are there to show us that the bond order corresponds to energy and inversely to the bond length. So carbon, each carbon atom has 4 valence electrons. So then in the molecular orbital diagram, we have 8 electrons. So we've got 2, 4, 5, 6, 7, 8. They have to pair up. So we calculate the bond order here. We're looking at bonding orbitals, 2, 4, 6. A total of 6 electrons. Minus 2 is 4, divided by 2 is 2. So the bond order is 2. That predicts that this is a stronger bond than between the boron atoms. The bond energy here is 620 as opposed to 290. Stronger bonds are shorter. The bond length is 131 picometers instead of 159. We go on to nitrogen. Nitrogen has 5 valence electrons. So you have 2 of them together, there's 10. So they fill up 2, 4, 6, 8, 10. And the bond order here is even higher, right? Because we're adding more electrons in the bonding orbitals. So here the bonding order is 3, and we experimentally determined that the bond energy is 946, even higher, and the length is even shorter. Any questions? For oxygen, fluorine, and neon, they use the normal molecular orbital diagram. So here we've got sigma 2p, pi 2p. These are switched from over here. So for oxygen, we've got 6 valence electrons, so a total of 12. Goes 2, 4, 6, 8, 10, 11, 12. And now the bond order is lower. And we see that the bond energy is lower and the bond is longer than comparing to nitrogen. Fluorine has 14 total valence electrons, and so they fill in like this. Bond order is 1. Neon has 8, so we get a total of 16 valence electrons, and that fills everything up and gives us a bond order of 0. Neon does not form a diatomic molecule. Any questions? I'll take that as a no. Oh, I forgot I had videos. Well, this will be a surprise. Let's see what they are. You want to do the long version or the short version? Short. We'll do the short one.
When liquid nitrogen is poured onto a magnet, the magnetic field does not affect the liquid. When we pour liquid oxygen onto a magnet, however, it is held by the magnet because oxygen molecules are paramagnetic. Paramagnetic substances have unpaired electrons.
Cool. Forgot about that one. We got to see that one again. Yeah, here we go.
When liquid nitrogen is poured onto a magnet, the magnetic field does not affect the liquid.
Pours right through.
When we pour liquid oxygen onto a magnet, however, it is held by the magnet because oxygen molecules are paramagnetic. Paramagnetic substances have unpaired electrons.
So it sticks. That's cool. Okay, let's see if we can get back to where we were. It would be fun to be able to do that in class, but it just takes way too much effort and time. So look at the molecular orbital diagrams for oxygen and for nitrogen. Oxygen has 2 unpaired electrons. That means that it's paramagnetic. It will be attracted to magnetic field. And as we saw in the video, liquid oxygen sticks. It gets stuck between the 2 poles of the magnet. Nitrogen is diamagnetic. All of its electrons are paired up. It has no attraction for a magnetic field. And so it just pours right through, like we would expect. If we, does that work? No, never mind. So we know from experiment, we saw it, that oxygen's paramagnetic, right? When we look at the Lewis model and the valence bond model for oxygen, there's no unpaired electrons. So here's the Lewis model. All of those electrons are paired up, aren't they? When we look at the valence bond model, we have, with this double bond, we have a sigma bond between the hybrid orbitals, and we have a pi bond up here, and then we've got orbitals with lone pairs. Everything's paired up. These models do not predict this observed behavior of oxygen being paramagnetic. Any questions about that? Okay, so draw a molecular orbital energy diagram and determine the bond order for the N2 plus ion. Do you expect the bond to be stronger or weaker than in the nitrogen molecule? Is this diamagnetic or paramagnetic? Okay. Well, first we need to think about a nitrogen atom and think about the valence electrons, right? So nitrogen has 2 electrons. Well, let's not put electrons in yet. Its valence electrons are in the 2p, that's a 2s, and the 2p, right? And how many valence electrons does it have? 5. So 1, 2, 3, 4, 5 valence electrons. And the other nitrogen atom has those same orbitals. But if we're going to make N2 plus, then this one needs to be an N plus, meaning it's lost an electron. So instead of putting in 5, we're going to put in 4. 1, 2, 3, 4. Everybody still with me? Mostly, at least. Then we combine these. So combining 2s orbitals, we're going to get a sigma 2s and a sigma star 2s. And so one's going to be lower and one's going to be higher. So this is our sigma star 2s, and this is our sigma 2s. And then the 2p orbitals combine, and they're going to make sigma and sigma star, pi and pi star. But what's the order? We're looking at nitrogen. Be careful now. This is the one that's reversed. So I didn't plan ahead very well, and I don't have any space there for my anti-bonding orbitals, so I'm going to just erase a little bit of that. So what we should think of as normal, and this is going to be all squished together, this is normal, very symmetrical. We've got sigma, sigma star, pi, and pi star. Okay, what did I do wrong there? I had too many boxes. These guys, there's only 2 boxes there. Now I erased my erasing. Shouldn't be possible. This should be 2 boxes.
Why are there only 2 boxes?
Because I started with 3 and 3 is 6, and so when I combine them, I can only have 1, 2, 3, 4, 5, 6. I can't increase boxes. I can just rearrange them. So this is normal, but we're in nitrogen. Be careful now, and so we need to switch these 2. So I'm going to erase those. And the pi bonding orbital is lower in energy than the sigma bonding orbital. So this is pi 2p, sigma 2p. This is pi star 2p, and sigma star 2p. How's that for trippy? So these, well, that's not a dashed line. These are coming from those 2p orbitals.
So the P has both sigma and...
Has both sigma and pi. And if you think about the pictures, we had them overlapping end to end. And so that makes a sigma orbital, like a sigma bond in valence bond theory, where it's symmetrical. And then when we overlap them side to side, then that's a pi orbital. Here's our nuclei, and we've got this electron density above and below. So this is pi, and this is sigma.
And sigma is only 1 box?
Only 1 box. There's three orbitals, right? And only one pair can overlap end to end. The others are just going to be sticking up and down and going in and out of the page. And so those can't overlap end to end. They have to overlap in a side to side, like a pie. Okay? So any questions about how I got that? Now we're going to take the total electrons that we have. We've got 5 over here and 4. 5 plus 4 is 9. So we're going to fill them in. I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. What's the bond order? So bond order, how many electrons in bonding orbitals? 2, 4, 6, 7, right? How many in anti-bonding orbitals? 2. So 7 minus 2 divided by 2. So that's 5 halves, or 2.5. The bond order for N2 was 3. Is this stronger or weaker? It's weaker because its bond order is smaller. Is it paramagnetic or diamagnetic? It's paramagnetic because we have an unpaired electron. Any questions? This is the sort of thing that you should be able to do. Not drawing the pictures, but if I give you a very simple diatomic molecule, you should be able to draw the molecular orbital diagram for it and calculate a bond order, identify if it's paramagnetic or diamagnetic, and be able to predict whether it's stronger or weaker than a bond in some other molecule where you can figure out the bond order. Okay? Now we're going to look at second period heteronuclear diatomic molecules. So here the two elements are not the same. So here's one of my favorite molecules again. No! So the mo for no is here. Oxygen is more electronegative, so its atomic orbitals are lower in energy than those for nitrogen. So here we have nitrogen with its atomic orbitals 2s and 2p. Here's oxygen with its atomic orbitals, and these are a little lower in energy than the ones for nitrogen because of electronegativity. So these combine in the same way. 2s and 2s make a sigma 2s and a sigma star 2s. And we've got sigma 2p, pi 2p, pi star 2p, and sigma star 2p. Now you might wonder, well, we said be careful now. Nitrogen does that other arrangement, and oxygen does the normal arrangement. Here we've got one of each. What do we do? Well, I wouldn't do this to you on a test, that's for sure. We're going with the normal. Why? Because that's what it actually does. I don't expect you to know that or be able to predict that. I'm just acknowledging that this is something I'm not explaining to you. So the lower energy atomic orbitals contribute more to the bonding molecular orbitals. The higher energy ones contribute more to the higher anti-bonding molecular orbitals. Nitrogen has 5 valence electrons. Oxygen has 6, so it's a total of 11. We get 2, 4, 6, 8, 10, and the 11th one goes in here. So we would predict that this is a paramagnetic substance. And what's its bond order? Well, we count up ones without stars. So 2, 4, 6, 8. So 8 in bonding orbitals, and how many in non-bonding, anti-bonding? 2, and 1 more is 3. So this is going to be like that N2 plus with a bond order of 2.5. Any questions? when you get things like hydrogen fluoride, so here we've got hydrogen, and here's fluorine. And the really funky thing about this is fluorine is so electronegative that its 2p orbitals are lower in energy than hydrogen's 1s orbital. Why? Because fluorine's very electronegative. It's very good at attracting electrons to itself. So what happens here is that one of fluorine's 2p atomic orbitals combines with the 1s from the hydrogen and makes sigma and sigma star. And then these other two just sit there. And so we end up with something like this.
How about the S orbital for fluorine?
Well, the s orbital, the 2s orbital for fluorine has a pair of electrons in it, and it's just going to sit there. Because it's so low in energy. The 2p is closer, and so this is going to interact with one that's closer in energy.
So then we just have
There's 6 electrons, 7 from the, I'm sorry, there would be another one down here that would just be the 2s from fluorine. That would give you the correct number of electrons.
But how do we distribute them into the bonding orbital?
Well, you'd start at the bottom and fill up. So there's a 2s over here from fluorine that's full, and that one doesn't participate in the molecular orbital, and these don't participate. And I don't expect you to know that. I'm just showing you, okay, this is a weird thing that happens. Okay, use molecular orbital theory to determine the bond order of the FO minus ion. Is the ion paramagnetic or diamagnetic? So let's start by drawing the orbital diagrams for fluorine and for oxygen. So we've got 2p and 2s. This is for fluorine. And we've got, okay, which is lower in energy, do you think? Fluorine. It's more electronegative. So I'm going to draw the oxygen just a little bit higher than the fluorine. So it's got 2s and 2p. And this is oxygen. And then when we combine these, we've got 2 elements that do the typical arrangement. We don't have boron, carbon, or nitrogen, so we don't have to worry about that. So from these 2s orbitals, we're going to get in a sigma 2s bonding orbital and a sigma star 2s. And from the 2p's, we're going to get a sigma 2p, and we're going to get a pi 2p and a pi star 2p and a sigma star 2p. This is our expected arrangement where we've got the sigmas on the outside and the pi's on the inside. The higher is always the star, the anti-bonding. So these are coming from here. So FO minus, how many valence electrons does that have? Got 7 from the fluorine, 6 from the oxygen. The minus sign says we have to add 1, right? So that's a total of 14 electrons, 14 valence electrons. Everybody okay with that? So it doesn't matter exactly how you put them in for the atoms. Fluorine had 7, 1, 2, 3, 4, 5, 6, 7. Oxygen had 6. 1, 2, 3, 4, 5. That was scary, huh? 5, 6. We need to put one more in. It doesn't matter which one we give it to. I think I'm going to give it to the nitrogen. There's no nitrogen. That would be fun. I'm going to give it to the fluorine because fluorine's more electronegative and electrons really like fluorine. It doesn't matter. What matters is I'm going to fill this in with 14 electrons. So 1, 2, 3, 4, 5, 6, 7. The next one is going to take its own orbital. 8. Now they have to pair up. 9, 10, 11, 12, 13, 14.
So we filled it in the same way as we filled the orbital?
We fill it the same way as we filled orbital diagrams when we were learning about the quantum mechanical model of the atom. You fill the lowest energy orbital first. Hund's rule says it will fill 1 electron per orbital with parallel spins. So if we think back to the quantum hotel, this is 2 beds, and if they can, they're going to have their own bed, and they're going to sleep right side up in the bed. When they have to share, they'll sleep upside down. But they'd rather not. So we're supposed to determine the bond order. So bonding orbitals, 2, 4, 6, 8. How many in antibonding? 2, 4, 6. And that's divided by 2. So 8 minus 6 is 2 divided by 2. So this has a bond order of 1. That tells us that this ion probably exists. Is it paramagnetic or diamagnetic? It's diamagnetic, because all the electrons are paired up. Any questions? Again, this example is something that you should be able to do. Well, what about those polyatomic molecules? We talked about ozone. This was the Lewis structure for ozone, where we had resonance. We had a double bond on one side, a single bond on the other, and this was how the Lewis structure represented that. But we said experimentally, we know that the bond lengths are the same on this side and on this side. And so it's actually more of a 1.5 bond. This is the valence bond model for ozone. And so we've got a sigma bond between hybridized orbital of this oxygen with a p orbital on this oxygen. Then we have a pi bond here between 2 unhybridized p orbitals. So that's this double bond. And then this oxygen is forming a sigma bond with the third oxygen over there. This is predicting a double bond here and a single bond over there. That is not what we observe. So both of these models are falling short. This is what the molecular orbital theory does. We get pi molecular orbitals formed between 3 2p orbitals. 1 p orbital on this one, 1 on this one, and 1 on that one. And they are delocalized over the entire molecule. This is what we observe experimentally, that the bonds between these 2 oxygens is the same as the bond between these 2 oxygens. So you do not need to be able to draw this picture. This is just me trying to explain to you why we even care about molecular orbital theory, because it explains some things that the other theories don't.
So the bond there is neither pi or sigma?
Well, there is a sigma bond here, but then there's also this delocalized pi bond. And so that's the kind of 1.5 bond. The other theories can't deal with that. Molecular orbital theory can deal with that. It can take electrons and delocalize them, spread them out, say, well, actually, they're kind of roaming about the whole molecule. They're not just stuck between two individual atoms. Another example is benzene. So these are this is the Lewis structure for benzene. The best we can do is to draw it with alternating double and single bonds. It's a 6-carbon ring, alternating double and single bonds, and each carbon has a hydrogen bonded to it. So you could put the double bonds like this, or you could move them over and put them like this. Experimentally, though, we understand that benzene has identical bonds between all of its carbon atoms. This is the molecular orbital explanation of benzene. It's delocalized pi orbitals. They're delocalized over the whole molecule. Benzene is highly symmetrical. It's got 6 identical carbon-carbon bonds. Molecular orbital theory explains this. Valence theory and valence bond theory and Lewis model don't. Any questions? Okay, so just a comment. Why do we even explain this to you? Most of the time, you're going to use the Lewis model or the valence bond model. They're great. They work for a lot of things. We just need to know that this molecular orbital theory, this model, exists, and it does explain what those others don't. And so as long as we can understand, looking at this, well, it's actually a combination, an average between them, more like 1.5 bonds all the way around, then we don't actually have to go look at this over and over again. We just said, okay, we talked about that, we know it exists, we're fine with it, now let's go back to our nice Lewis structures.